Hello everyone, welcome back. If you're attending this series, or welcome to MI2 if you're attending this for the first time. My name is Janaki Ram. I'm the presenter for the session, and I'm pretty excited to bring you getting started with Azure ML Pipelines. So before I go further, let me set the stage by explaining what is MI2. So MI2 stands for Machine Intelligence on Modern Infrastructure. Every track will have sessions dedicated to the topics. The machine intelligence track will have sessions on IoT, AI, ML, cognitive computing, and so on. The modern infrastructure track is primarily focused on Kubernetes and cloud native technologies. Every webinar is complemented by a tutorial, code snippets, and of course, you have access to the recorded video, which will be uploaded to my YouTube channel. This is completely independent and a neutral platform to bring emerging technologies to you. So today's session is a pretty interesting look at the ML ops and machine learning pipelines to build very consistent, repeatable workflows. So the agenda for today's session is a quick overview of Azure ML platform. I have done a full-blown series on this last year. You can look up for a session on my YouTube channel that has an end-to-end demo on how to use Azure ML to train, build, and deploy machine learning models. But if you're attending this for the first time, or if you're not familiar, I'm going to kick this off with a quick overview of Azure ML. Then we'll take a look at the ML pipelines and how Azure ML pipelines help us build very complex workflows for machine learning. So let's get started. Now, if you're not familiar with machine learning, basically every ML model has two lives. The first life is where it gets trained. So we take historical data, we split that into training and testing data set, and then we choose an algorithm, apply that to the training data set, and we test the results or the predictions against the test data set, and we iterate it over this process multiple times till the outcome of the evaluation is satisfactory. And once the evaluation is satisfactory and is up to the mark, then we move that into production, and the model is set to be in inferencing. So in inference, we send production data for the model to perform predictions. And this is the second life of the machine learning process. The first one is training, the second one is inference. Now, to do both the training and inference, you need a robust platform. And there are multiple individuals, teams, and personas that get involved in this process. For example, to really set up the environment and to run the right infrastructure, you need the DevOps team. So they provision VMs with GPUs, they install software like Anaconda, CUDA libraries, TensorFlow, PyTorch, scikit-learn, the entire data science stack. And they hand it over to the developers or data scientists who actually train and tune the model. And once this is done, the focus goes back to the DevOps team where they deploy the model and scale the model. And for them, this is not very different from scaling a web application or any other workload. So if you notice, there is a shift between DevOps and data scientist as a part of setting up the infrastructure and managing the life cycle of a machine learning model. So we need a platform to basically handle this effectively. And instead of the data scientist relying on the DevOps team for provisioning and configuring or to deal with deployment, they need to be empowered with a set of APIs that they are familiar with. For example, in order to set up a GPU-based VM, the data scientist should have a Python API to basically spin up the entire environment. Maybe that's running an NVIDIA GPU-based VM, and then it is running a Docker container that is fully loaded with the data science stack. So the developer and the data scientist should be empowered to perform this entire life cycle programmatically, all by themselves without much dependency or reliance on the DevOps team. So to make that happen, there is a new product offering, and there is a new platform that is called Machine Learning Platform as a Service that is gaining a lot of attention. So the ML pass, like a typical development pass. So if you are familiar with Google App Engine, Azure App Services, Heroku, IngenueYard, and Cloud Foundry, you know what a pass is. Developers bring their source code and walk away with a URL. That is the promise of pass. Now, what a machine learning pass promises to the data scientist and the developer is the entire platform that abstracts away the life cycle involved in developing a model, all the way from provisioning the infrastructure to scaling it on demand, is done by Python SDKs or through R SDK, or basically it is an integral part of the data science environment. So the machine learning pass abstracts away the infrastructure plus the data science stack and exposes enough APIs for the developers and data scientists to deal with the entire life cycle. And typically this machine learning pass is exposed via a dashboard, a CLI, and of course the Python or R SDK. Now there are quite a few machine learning pass offerings available in the market. There is of course Azure ML, which is the focus for today. Then there is Amazon SageMaker. There is Google Cloud AI. Then there is Floyd Hub, and there is Paperspace Gradient, and there are many other such offerings that promise similar capabilities. Now, Azure ML is actually a PaaS. It sits on top of the existing building blocks of Azure, like VMs and storage, networks, a container infrastructure, and exposes the most friendly API to the data scientist so that he can use his favorite tool, something like a Jupyter Notebook or a PyCharm or a Visual Studio Code environment, not just to write code, but also deal with the underlying nuts and bolts of the platform. So that is what is Azure ML. Now, going back and revisiting the ML workflow, if you are familiar with developing machine learning models, you know that there are multiple stages of the process. You have to prepare the data, because in most of the cases, the data set that we get is either incomplete or has a lot of noise or inconsistent. There could be missing values. There could be a lot of cleanup that needs to be done. For example, the date formats and the way the data is currently encoded. So there is a lot of effort that goes into preparing the data. And once the data has been completely cleansed and prepared, then it goes into the training phase, where the actual algorithm gets applied to the prepared data and the model starts to evolve. And once the model has been thoroughly evaluated and fine-tuned, it goes into packaging. So packaging is where you either put that in a Docker container image or you move that to a model management environment, and ultimately it goes into an inference cluster. And then it gets validated with some real world data, and it is finally deployed in a highly scalable cluster, something like a Kubernetes cluster or a fleet of VMs exposed by a load balancer. And it is constantly monitored to see how the performance is, how many requests per second are being sent to this model, and what can be done to enable high availability of the model. So these phases are completely independent and they need to be treated independently. For example, the data preparation in itself could be a massive exercise. For example, you could get 1 terabyte of a data set, and to effectively prepare the data, clean the data, normalize the data, you need a Hadoop cluster or an Apache Spark cluster. And the output of that step will become the input for training the model. And for training the model, you can't use the cluster that was used for preparation. You need to spin up a very powerful fleet or a Kubernetes cluster or a set of VMs powered by Tesla P100 or K80 NVIDIA processors, GPUs, and the training gets done on that. Then for packaging and validating, it'll happen in a separate set of VMs or separate set of machines. Then deployment takes place in an inferencing environment, typically running Kubernetes or Mesosphere or any of the infrastructure related environments. And finally, there is model monitoring. So each of these are completely independent and demand very dedicated, exclusive environments. So ideally, we need to be able to stitch these phases in a very loosely coupled fashion. If the dataset is small and if the processing power is not demanding, you can pretty much do all of this in a single machine. But if you're dealing with complex models related to image processing or video analytics or some of the advanced models in terms of convolutional neural networks or recurrent neural networks, then you definitely need to have a full-blown pipeline that is associated with multiple compute and storage environments. And that's where we have the Azure ML pipelines. So Azure ML pipeline basically gives you a very loosely coupled but highly independent executable workflow of multiple ML tasks. So the best way of visualizing Azure ML pipeline is, imagine if you're a data scientist, you're writing your Python program in units of functions. So you will write a function to prepare the data. You will write another function to train the model. You'll write another function to package and deploy the model. Now, these functions are a part of, let's say, Python modules, and you can invoke them and you can call them in a sequence to execute all of this. This is fine if you're running it on a developer workstation with a tiny data set and a very simple algorithm. But the same thing cannot be used when you're dealing with highly complex data sources and highly complex deep learning or neural network models. So that's where you need a robust infrastructure that will help you take the same modular approach but can scale out independently. So Azure ML pipeline is essentially a collection of multiple stages, and each stage represents an independent task that is responsible of doing one and only one task. For example, prepare data will only prepare the data. It will take a large data set as an input. It will run some data preparation job, and the outcome is a data set that is ready to be fed to the training program or the training stage of the pipeline. Every stage will obviously have dependencies. For example, when you're dealing with an Apache Spark cluster, you need to have a lot of dependencies and a very different set of requirements. The same thing when it comes to training, you may want to have TensorFlow or PyTorch or MXNet or CNTK as your framework. So every stage has its own set of dependencies and they need to be managed well. So one size doesn't fit when it comes to ML, and you cannot generalize the infrastructure. You need specialized infrastructure, both in terms of hardware and software, for each of the stages that you're using for the pipeline. So what Azure ML does is it basically takes the multi-staged pipeline concept and gives you an orchestration mechanism to put all of them together, and a very robust and very reliable way of connecting them either in parallel or in a sequence and executing them in a highly managed environment. So you don't need to worry about a lot of nitty-gritties, nuts and bolts of the infrastructure. So when prepare data stage kicks in, it automatically spins up an Azure Databricks environment, brings a Spark cluster, and runs the entire data prep job on that. And once the data prep job is done, it basically dumps the cleansed prepared data set to an Azure blob and then moves on to the training phase, which will pick up where the previous stage has left from, and it will start processing. So basically, Azure ML pipeline is a very consistent, repeatable workflow to bring in multiple stages of a pipeline and to effectively orchestrate it to manage the end-to-end lifecycle of the model and your project. Now, the best thing about Azure ML pipelines is once you define the pipeline through code, you can publish the pipeline as a REST endpoint, which means if you want to execute the pipeline all over again, you just need to invoke a REST endpoint and it will essentially trigger the pipeline, which means every phase will be automatically run. So every time you notice drift in the data, in the model accuracy, for example, the model deteriorates over a period of time because the quality of data is not good, or the schema has changed, or the model needs to be retrained. In that case, you basically dump the raw data set, which is an input to the prepared data, and then you trigger the Azure pipeline through a REST API, which will essentially kick off the pipeline run process, which will create the model, and you can pick up the model again from Azure storage and move it over to your inferencing environment. Or you can also set up model management effectively in a way that you can do blue-green deployments even for models coming out of the pipeline. So that's the high-level overview of Azure ML Pipeline. So at a high level, Azure ML Pipelines will do 4 things. One, it can do data prep. This can be anywhere from using pandas to using FFmpeg to split a large HD video into individual frames and saving each frame as a JPEG image, to dealing with massive data sets coming from different parts of the world, or extracting it from an ETL job connected to a data warehouse. It can perform anything. Sky is the limit, literally, because as long as you have access to the underlying infrastructure and you know what you want to do with it, you can use any technique for data prep. Then comes the training configuration. So you will define how your training configuration would look like. For example, you can ask Azure Pipelines to create a configuration that says, hey, give me a GPU powered VM. Azure has a lot of VM categories and families, so you can choose the right image and the right configuration. And you can also have a Docker container image built exclusively for your training or prep job. So you can actually create that configuration, and then you can start training the model based on the custom configuration that you have requested for. And you can also run validation, simple scoring and evaluation. And once that is done, you can move it over to deployment, which will run in a very scalable environment. So all of this is orchestrated and effectively managed by Azure ML Pipelines. So enough of theory. I'm pretty excited to show you a couple of demos. Even if you're not very familiar with machine learning, or even if you're not familiar with ML pipelines, you will still be able to understand this concept. So the demo for today is based on a very simple data set. It's called the Pima Indians Diabetes Database. Basically, the goal of the model that we're going to train is to find out if someone has the diabetes or not, based on a set of input features. For example, how many pregnancies does the individual has, and what is the plasma glucose concentration, what is the blood pressure, what is the insulin level, 2-hour insulin, the metric for that, and then the BMI and diabetes pedigree function, of course the age, and then we'll actually predict whether this individual is prone to diabetes or not. So this is the data that we're going to use, and I'm actually taking the same data set available on Kaggle. So that is the input, and what I want to do now is I want to show you a very simple program which will look like this. So this is an extremely simple scikit-learn model, nothing complex or nothing fancy about this. So we start by importing NumPy, Pandas, and scikit-learn. Then we create a data frame from our CSV file. And by the way, this is how the data looks like. It's exactly the same data set. So we load that into Pandas, we create a data frame, and then we extract the features and the label. Label is the outcome, which is a 1 or 0. And then I use a min-max scaler just to bring in some kind of normalization. So basically it takes all the features and converts them into a value between 0 and 1. This is to avoid any outlier or to have any kind of an inconsistent data. So we normalize the data by scaling them to a value between 0 and 1. And then we take the trained we take the normalized data, and then we pass it on to the split, where I'm actually splitting this based on 33% goes to test data and remaining goes to the train. And to get consistent results, I'm setting up the seed. So this will basically split the data into a test data set and the train data set. So X train and Y train will contain the features and labels of the training data set. X test and Y test contains the features and labels of the test data set. And then I simply call logistic regression and pass the training data set, and the result comes with the scoring of that. And once this is done, I basically move to prediction, where I feed a sample NumPy array, and then I apply the same transformation, because we have to bring the data to the same level playing field as the training. So I'm basically taking the same scalar. Here we're calling fit transform, and here we are calling transform. This is basically meant for inference. So now we are taking the input data, passing it to the same scalar to normalize the data, and then we are finally calling the predict on the same model object to get the prediction. So the prediction is either a 0 or 1. Pretty straightforward. So we can even run this and it prints a 0 or 1. Okay, so my environment is not set. So this is the high level Python program that I wanted to show you. Pretty straightforward. And now what we'll do is we'll actually take the same program, same approach, and do this from two approaches. One is, how do we build a pipeline using Azure ML Designer? That's a very new tool. It is still in preview, but a very powerful technique to create pipelines. Then I'll show you a Jupyter notebook where I programmatically create the entire pipeline and run it on top of Azure ML pipeline infrastructure. So let's switch to the demo. So I want to show you the new Azure ML environment. So this is how you basically get started with your managed ML projects. So Azure ML comes with notebooks. You can actually create a new Jupyter notebook. There is an Auto ML. So Auto ML is a great technique to train models without writing a lot of code. So you need to pass some tabular data, and Azure ML will come out with a linear or a logistic regression based model. And then there is Designer, and this is what I'm very interested in. These are the things that you author as a data scientist. Then there are some assets like data sets, experiments. So an experiment is a collection of multiple trial runs, and of course pipelines, models that you register, which are the outcome of the actual training that you run, and endpoints that are exposing the models as REST endpoints for inferencing. So as I mentioned, I'm going to do two things. One, to design a pipeline using the visual interface. And then we'll switch to a Jupyter notebook to see how we can programmatically do that. So let me show you how simple it is to build an ML model with the designer. So remember, we have a data set. And this is the diabetes data set that's in my local disk, right? So it all starts by registering the data set. So when I click on data sets, create data set, you choose from local file. Tabular is a TSV or a CSV file, basically the comma separated value file. Give a name and move to the next step. And here you can browse and upload the data set. So I've already done that. So this will give you some interesting things like, the column names, the schema, and so on. Basically, you are registering a CSV file as a data set. And registering this as a data set will give you a lot of advantages. This becomes available to all the assets in the workspace. So the way Azure ML functions is you start with a workspace. So I have a workspace called demo. So once I register a data set, basically it becomes available to anything that is running inside the workspace. So that is the advantage. So we started with that by registering the data set. And let me rename this to diabetes. So this is my designer environment. Now, the first step that I'm going to do is to drag and drop my data set. So the data set that I registered shows up here, and you also have some public data sets, some samples like the New York taxi data set, weather data set, and so on. So I'll start by dragging and dropping the data set. Once I have this, I can basically right click and visualize. So let me get to that. So first we have the data set, and then I'm going to choose select the columns in the data set. This is optional, but I want to show you how this works. So now what happens is, this is a database or a data set that I want to filter upon. For example, I don't want to have all the columns used in my training. So this gives me a nice opportunity to either include all the columns or to exclude. So now I can actually say, with rules, all columns. So later on, if I really want to do anything, I can come back and filter on the data. So select columns in the data set. Now this can be run in a completely different cluster environment. So here I have registered a compute environment. Let me open another tab and show you that I have already registered a compute environment. So the compute environment essentially means the compute infrastructure for us to run multiple stages of the pipeline. So in the compute cluster, you notice that there is a demo cluster, and this demo cluster is currently auto scaled and it has gone back to 0. So once we kick off the pipeline, it will get restarted and it will move from 0 to 1 or 0 to 2, whatever was the size that we mentioned. So currently it has 0 provision nodes, but as soon as the pipeline kicks off, this compute cluster will wake up and it will become the infrastructure for us to run every stage of the pipeline. So we choose that and save it. Now imagine this could be a Spark job, an Apache Spark job. And if you really want to run the data prep stage here, and you don't want to run it on a simple compute target, you can always create a new compute environment. For example, here you can say new and choose a virtual machine type, or it could even be a Databricks environment. So you can basically define a VM or a cluster of your choice and use it independently for every stage. But for now, I'm going to use the same default compute target that I can actually set here. I think somewhere here, I can define what is the compute target for my entire pipeline. This is the default compute target. So if I don't change the settings, that means every stage of my pipeline automatically runs on that compute target. So once we have this, then the next step is to basically split the data. So we are going to create a test and train data set. So I'll connect the select columns module to split data, and the first output data set, I want it to be 70%. So I choose that as my training data set, and 30% goes to the test data set. And if you notice, this module has two outputs. So which means it has one output for train and one output for test. So with the data currently split, my next job is to basically create the actual model. So here in the palette, there is a machine learning algorithms section. So I'm going to grab the two-class logistic regression. This is what we actually need. So it's the two-class logistic regression. And then I'm going to drag and drop the model training, train the model module. So train the model actually takes the algorithm, which is the binary classification or the logistic regression, and then it takes the input from the split data set. So at this point we have So this is showing an exclamation because we need to basically choose the actual column um, responsible for the label. So since we don't have the labels, the header, I choose 9. 9 basically represents the last column, which is the outcome. So we are actually telling, train the model and use this as the label. Now, once the training kicks off, we need to basically score the model. So there is a score model and evaluate model option. So you pass the output of the training model to score the model. And how does the scoring happen? It has to have some input from the test data. So we connect the test data set to scoring the model. And finally, we want to evaluate the model against a set of metrics. For example, the confusion matrix, F1 score, ROC curve. I don't want to get into the details, but those are some of the techniques by which you evaluate a model. So now you can actually connect the score model to evaluate model, and this basically represents your entire pipeline. I really like the way Microsoft built this canvas. It's pretty intuitive, and even though this is a very simple pipeline, it essentially reflects the real world scenario. Now, once you have the entire pipeline defined as a draft, so this is called the draft pipeline because we are still allowed to make changes. For example, you can click on visualize, and visualize shows you the data set within the canvas. This is the same data set that I grabbed from Kaggle. You can also look at this for the the 70% 30% split as a part of the split data set module. So you get an idea. Now, once we are convinced that this is the pipeline and it looks good, and we associated every phase of the pipeline with a different compute target, and once we are convinced, we'll go ahead and click on submit. Now, once we click on submit, you need to choose an experiment. So an experiment is a collection of multiple trials, multiple runs. For example, you want to change a hyperparameter and run it all over again. It doesn't create a new experiment, but it becomes one of the runs. And you're targeting demo cluster as the compute target. You can also create new and basically start a new experiment. But let's choose an existing experiment and click on submit. Now this is going to take pretty long because it has to bring up the compute cluster and so on. So this is how the final output would look like. Assuming I ran the pipeline, I have switched to my other project. They are identical, they're exactly the same, but to save time from really submitting this pipeline and waiting for it to finish, I've already run this once so that we are ready to actually see that in action. So exactly the same thing. Now, if you look at the evaluate model, the outcome of this, it'll show you all sorts of techniques to basically evaluate the ROC curve, precision recall curve, lift curve, the threshold for confusion matrix, if you really want to do that. So all those will show up here. So pretty insightful and very powerful. And you can also visualize the scored data set. So this actually tells you, what is the scored probability on every data point, and so on. So now, this is actually done. So the pipeline has been submitted and Azure has orchestrated every step. Now, what happens once this is done? What happens once the pipeline is executed? So what it actually leads to is the creation of a model. So basically, let me again open this in a different tab. So when we run the pipeline, once the pipeline has been successfully done, it basically creates a model. So this model has been registered with Azure ML platform, and now this is ready to become a deployment. So that is the outcome of this entire process. Now, once the pipeline has been successfully executed, I can create what is called as an inference pipeline. Now, an inference pipeline takes the model and creates a pipeline to take it into production, which is basically hosting it in a compute cluster and exposing that as a REST endpoint. So again, this is pretty time taking. So what I've done is I've already created an inference pipeline, beforehand. So that inference pipeline would look something like this. So it takes the data set, it takes the web service input, then it takes the model that is pre-trained and scores the model. Scoring the model is again basically inferencing, and then sends the web service output. So this is the inferencing pipeline, which is the second phase of our pipeline. Now, once this is done, you can click on deploy and choose an existing or a new real-time endpoint. So what I have done is for the inferencing, I have actually created an Azure Kubernetes cluster. So this Azure Kubernetes cluster is currently running on 3 nodes, and it has 18 or I think 12 cores, if I'm not wrong. So we can even explore that environment. So this AKS cluster has pretty decent power. I think it runs 3 nodes with 4 cores each, and every node has 4 GB of RAM. So it's a pretty decent AKS cluster. So what we'll do is we'll actually associate our inferencing endpoint with this AKS cluster. Now, something magical happens here. So it takes the model, wraps it around a Docker container, turns that container into a pod, and exposes that as a web service, as a REST endpoint inside the Kubernetes cluster. And that's what shows up here. So ultimately, when we click on endpoint, you will see that there is something called diabetes real-time inference endpoint. And this endpoint is published by our pipeline. So you can actually populate some test data. So this is the web service. Click on test. Excuse me. So it basically scored the output with 1. Now, if you really want to try this, you can also copy and paste some Python code. So it will give you a paste command. So let me try. I think I have all the libraries. So we'll paste this sample code inside infer.py and try to run this. There we go. So now we have gone end to end. Basically, this is the designer. This is the designer that we are using, and this is the inference code. So we are able to effectively run the end-to-end application, or rather the build, train, deploy, infer, and without writing any code, I was able to design a complex pipeline. Not so complex, but the same technique can be used for any other convolutional neural network that deals with images or audio files or video analytics. It doesn't matter, but we can actually build a pretty decent model just by using the same technique. So that was the first approach. Now, this is almost like Visual Basic for machine learning, right? You drag and drop, double click, write some basic code if required. Otherwise, you choose some options, push a button, boom, you have an endpoint. But many expert data scientists and many power users don't like the canvas. They want raw power. They want access to the infrastructure, and they want a lot of control. So that's exactly where we have the Python SDK. So now let me show you how this actually works. So, so what we'll do is, the code that I have shown you, I'll turn this into multiple stages of the pipeline. So effectively, this has just 2 stages, right? Let's call this, so this is basically start train. And here, from here, it is start prep. So start prep, end prep, right? So this is one stage of the pipeline, and just training the model is the other stage of our pipeline. We will leave out inference for now. No, we are not going to perform this step, which is predict, but let's take this small program, which is complete in itself. It actually does some data prep because we are applying a scalar and normalizing the data, and then we are passing it through a training algorithm. So technically, this is a complete end-to-end working legitimate machine learning code. So now, and it also has two individual decoupled stages that will turn into a pipeline. So so here I created multiple directories. So I have, if you look at the data directory, we have the CSV file. Now if you look at the prep directory, there is prep.py. So I'll show you the code for that. So we have this already running. I think it is there. Okay. So this is prep.py. So prep.py, basically takes some inputs, where to store the train data set, test data set, and the scalar file. And it takes the raw data set. It basically does the split, 70-30 split. And then it saves the train and test data, and also the pickled or the job lib serialized version of the scalar. So we effectively split the prep job into an independent module. This module accepts one input, which is the raw data, and gives us three outputs, which is the train data set, test data set, and a serialized scalar that is important for us to apply during inference. Because whatever scalar that we apply here should be the same scalar that we apply during inference. So we cannot change that. So scalar is also trained technically on this data set. So we want to serialize that and save it. So this is prep. Now train accepts the output from the previous stage, which is prep, and it takes train and test as the excuse me, train and test as the input and model as the output. So it basically takes these arguments, grabs the train and test, and applies the logistic regression on that, and then writes the model, the pickled or the job-lib version of the model back to the output, which is the storage of Azure. So pretty decoupled and very loosely coupled stages. So to summarize, the prep takes the raw data set and emits these three. The train takes the output of the previous stage, which is train and test, and emits the model. We don't need scalar for now because we'll actually apply it and use it during during the inferencing. So now let's switch to the Jupyter notebook. So here, I will launch the Jupyter notebook, and here I have the diabetes Jupyter notebook. Now, don't get overwhelmed. It's quite a bit of code, but very easy to understand. First I import all the libraries required for Azure ML and ML pipeline. So, this step basically make sure that we have all the dependencies in place. Then I connect to the workspace. So the workspace that I'm going to connect is already configured here. So when I actually do config.json, this file is utilized by the the environment. So it basically takes that and automatically authenticates based on the config.json and my Azure CLI credentials, and it gains connection to the workspace. And this workspace is what I mentioned here, which is demo. So once it grabs the workspace, it needs storage because that's where the input and output will go into. So there is a default Azure storage associated with the workspace. We grab that, and to that we upload the data set. So when we actually call upload file, we are basically grabbing the CSV file from the local hard disk and uploading that to the storage available for the workspace. Not only that, we will actually register this as the data set. I remember uploading a file is not very helpful. You need to register that as a data set to make it centrally available to all your modules, all your remaining workspace assets. So I not only upload, but I also turn this into a data set. So once the data set is ready, I will basically choose the compute. This is the storage part, this is the compute. So I'm actually asking Azure ML Pipeline to choose a demo cluster. And interestingly, demo cluster is already available to us. So if you look at the compute, demo cluster is already there. So now this will check if it is already there. If it is there, it will attach itself. Otherwise, it will basically create the new cluster. So at this point, we have the VM and the storage. Then I need some software to run on top of this. So here, instead of using the VM directly, I'm actually asking Azure to create a Docker image. So this Docker image is coming from the Microsoft registry. So it is basically the Ubuntu 1804 image. It grabs that image, and on top of that, it will run Anaconda Conda install to get pandas, scikit-learn, and numpy, and some pip packages like joblib, Azure ML SDK, and FusePy. These are the dependencies for my prep and train phases. So this is how I define software. Once this is done, I define how my data flows, right? For example, raw data contains the original data set. Train data and test data contain the split. Scalar contains the min-max scalar serialized version. Model file ultimately contains the fully trained model. So I define all of them using what is called as pipeline data. So pipeline data is a specific type of data set which is meant to connect the dots. Now I'll actually show you how this looks. Okay, let me complete this and then I'll switch to the canvas again. So now we have defined the intermediary data that flows from one stage to another. Then we start the preparation phase. So in preparation phase, we are saying that the source directory is prep. So you can actually see it here. So ls prep, so prep.py. So grab prep.py, pass the train, get the output as train data, test data, and scalar. Input is raw data. Output is this. Compute target is what we defined earlier, which is the AML compute, which is our demo cluster. Run configuration is the software Docker configuration that we defined here. And then source directory is this. LO reuse is true, which means if we don't touch anything, this stage will not occur again. It will basically cache the results and we will move to the next one. Very useful to save time. So once we execute this step, what essentially happens is it takes the raw data set and emits the train, test, and the scalar output. Now we take that as the input here, train and test data, and ask this phase to emit the model file as the output, and everything else remains the same. Use the same compute target, use the same software configuration, LO reuse is equal to true. And then we create a list of step 1 and step 2. We associate these steps with the pipeline, we validate it, and we run the pipeline as an experiment. And once the experiment is done, we basically grab the final output, which is the model.joblib coming from the second step, scalar.joblib coming from the first step, and copy it over to the local directory. So once this is all done, you'll actually notice that these two files come and sit in this directory. This execution takes about 40 minutes, so I'm not going to really run that. But I can technically keep hitting shift enter in every cell, and exactly 40 minutes from now, or slightly lesser than that, I'll actually have the entire workflow or the pipeline ready. Now, if I go to the experiments and click on diabetes run, so this is what I mentioned here. So diabetes run is the experiment name under which I'm going to have all the runs. So I have already executed this as a part of my dry run and preparation. So one run was completed. And if you actually look at the run and look at the graph, this is what I want to show you. It's a pretty powerful way of visualizing how our pipeline looks like. So this is the raw data set. Raw data set is fed to the prep step, and prep step takes raw data as input and emits train data, test data, and the scalar file. We are not using it as an input to the next one because this is important for the inference and not the train step. Then train step takes the train and test, runs the scikit-learn logistic regression on it, and also scores the model against the test data set and emits the model file. So model file is what is the output, and scalar file is the output from this. And you see green tick marks, which means both the steps have been successful. And this is just a visual representation of the Jupyter notebook where we defined step 1 and step 2, and it shows up here. So these are the steps, prep step and train step. They are completed. And if you even further drill down, if you go to prep step and look at the metrics, if it is generating any images, all of that, and particularly the output and logs. So you'll actually notice that these are the raw files that this step has generated, and we can also look at the logs. So this log shows you that the experiment has completed successfully. So it's a pretty insightful way of understanding how your entire pipeline has been executed. So this is a very powerful technique if you don't want to use the previous visual designer, and the SDK is self-explanatory. It took me about 3 hours to build this entire demo. So not very difficult. You just need to understand the mental model of creating the pipeline and then decide which steps you want to include and then go about writing each step independently. Now, the beauty of this approach is I can create a different compute target and a different run configuration for each of these steps. For example, if I want to run prep on an Azure Databricks Spark cluster, it'll have a dedicated compute and run configuration. And for train, if I want to run it on a different compute environment, I can define another compute and run configuration and associate it with this step. So completely decoupled, completely independent, and can have its own set of compute and software configurations. But the beauty is data will still flow between each of these stages, even though they are running in very different, completely isolated environments. It will still be able to connect the dots and flow the data from one stage of the pipeline to the other stage. So that was the demo. Now that almost brings us to the end of this session. I want to thank our sponsors, Google Cloud, the New Stack, and by the way, I'm starting a series on the at New Stack, which will cover everything that I discussed with the step-by-step code snippets and a GitHub repo, so you can actually grab this and try it all by yourself. I want to thank Foghorn, Portworx, who are sponsors for this webinar series. And I also want to make an announcement. Starting this month, I am turning this into a monthly series rather than twice a month series for various reasons. With the COVID-19 situation, most of my customers want additional time from me, and things are becoming pretty demanding. So unfortunately, it is taking a toll on me, and I'm becoming very busy. So I have decided to run one webinar per month from now. So the next webinar most likely will be on Onyx, which is Open Neural Network Exchange. So stay tuned for that announcement, and I'll see you in the next webinar. Thanks once again for joining me for the MI2 series. I'm committed to bring you the latest and the greatest from machine learning and cloud native world. Thank you.